Welcome to Gautam classes, students. Today is our topic work done in reversible isothermal expansion. So, look, we studied about the work done in reversible process, irreversible process. So, here now, particularly, we are going to study work done in reversible isothermal expansion. So, as you know that, so here, first thing we have to know that in isothermal expansion what is happening, you all is knowing very well. In isothermal condition, what thing is constant? In isothermal condition, temperature is constant. What? Temperature is constant. So what about the change in temperature? Change in temperature will be zero. And one more thing, what about the change in the internal energy? That will also be zero in case of isothermal condition. So what about the first law of thermodynamics? In that delta E is equal to the Q plus W. So in case of isothermal expansion and reversible process, what about the delta E? That is the zero. So we can write here zero is equal to Q reversible, and that is the W. That means further what we can say here, we can say that W is equal to minus Q reversible. This a thing. And you all is knowing that very well. What about the work done formula? Work done formula is P minus P dV. That we can write here. So minus Q reversible W is equal to what? Minus P dV. Now we are going to consider one thing is here. That I am giving the equation number 1. I am going to consider, let's suppose that, let suppose that 1 mole ideal gas, 1 mole ideal gas expanding reversibly in isothermal condition. In isothermal condition, you all is knowing very well, if that is the ideal gas, so definitely it should follow the ideal gas equation. What is the ideal gas equation? PV is equal to nRT. So in place of P we can write the nRT upon V. Because of we are taking the number of mole is 1, so directly we can say that RT by V. So that P value we can substitute in equation number 1. When we are going to substitute in equation number 1, directly we can say here Q reversible W minus RT upon V dV. That I am giving the equation 2nd. So look, now I am going to integrate that equation 2nd. And for that expansion, I am considering those are the initial volume is Vi and final volume is Vf. So Vi to Vf. And here what is given, that RT by V and dV. So RT will come outside, Vi Vf 1 by V dV. So by that directly what we can say, that RT ln V and initial volume and final volume, that is the by the integration rule. So final limit minus initial limit, so directly I am going to write here Vf by Vi. That thing we can write. This thing. So further, what if that ln we want to convert into log, what we can say, that here Q reversible is equal to W is equal to what? minus 2.303 RT log Vf upon Vi. This a thing. So that is our final expression. Those are the work done in what? Isothermal reversible expansion. And you know very well, if that is the ideal gas, so definitely it should follow the what law? It should follow the Boyle's law, Charles law, and ideal gas equation. So according to the Boyle's law, what you are knowing that PIVI is equal to what? PF and VF. So in place of VF upon VI, what we can write? In place of VF upon VI, we can write the PI upon PF. Or we can also write that in Q reversible is equal to what? W is equal to minus 2.303 RT log PI upon PF. This a thing. So hope all the students got the idea how we are going to derive that expression. So here what type of question is coming? Sometimes they are giving the initial volume, that one, final volume, that one, it is expanding reversibly isothermally. So what is the work done? What is the heat exchange in that condition? So heat exchange, that is given that Q reversible, and that is the W. So hope everything is clear that. And thing is coming somewhat work done in free expansion. What is the work done in case of free expansion? If free expansion is going on, that means free expansion means there is external pressure is zero. What is the external pressure? In that case, external pressure is zero. That means surrounding is not opposing the system to expand. So system is not having any problem for the expansion. That means external pressure is zero. If external pressure is zero, what about the temperature? Temperature remains constant. So system temperature is not going to change. So change in temperature will come zero. If change in temperature is coming zero, so what about the change in internal energy? That will be the zero. So how many quantity will become zero in that case? Change in internal energy is zero. If external pressure is zero, so you know that work done formula P external dV. So in that case, work done will also be zero. If change in internal energy is zero, work done is zero. So what about the heat exchange? Heat exchange will also be zero. Why this will be the zero? Because you know that according to the first law of thermodynamic, delta E is equal to Q plus W. If these two quantity is zero, delta E and W, so Q automatically will become zero. So always you have to keep in your mind, in a work done in free expansion, three physical quantity will be zero: change in internal energy, work done, and heat exchange. That means if work done in a free expansion is going on, so work done by the system will be the zero. Internal energy will not change. That means whatever internal energy in the initial state, same internal energy will remain the system in its final state. And heat exchange is also not possible. Now we are going to compare the work done in reversible and irreversible expansion. So look, sometime question is asking what about the work done in case of reversible expansion and in case of irreversible. So look, you know that those are the reversible process. It is going to complete into the several sub step. That means infinite number of sub step is involving to complete the process. But what about the irreversible process? It is completing with a finite number of step. So that I am showing here irreversible, and that one is showing for the reversible. So look, that reversible process is completing through the several number of sub-step. So definitely here system is going to do the more work, but here system is completing into the only one sub-step. So initial that one, final is this one. So always you have to keep in your mind, those are the reversible work done. It is a greater than the irreversible work done. What is it? Reversible work done always greater than the irreversible work done. Why this thing is happening? Because of those are the reversible process. It is completing through the infinite number of sub step, but those are the irreversible process. It is completing through the final number of steps. Just to imagine, suppose that there is a one story building, so that is the ground floor, this one is the first floor. You can go just in a one time, just a jump in one time. After that you are going by the step, that is the first step, second, third, fourth, sixth, seven, eight, like that several number of step. Or you are going by the lift. When you are going by the lift, so work done by the lift, and if person is going by the steps, so which one is going to do the more work? Definitely those are going through the these steps. So work done by the lift, it will be the less as compared to the when we are going through the step, because of here several number of small steps is involved. But in that case there is initial and final, directly it is going. But we are not considering here. Some student will say that sir, first floor, second floor, third floor, fourth floor, all that floor our lift is going to stop. I am considering only one floor, first floor to second floor. So look, when we are going first floor to second floor, lift will go directly without any stopping. That means final, initial and final state. But when we are going by the steps, what is happening? We have to go by one all that step. There is very small number of step is coming under that. So work done in that reversible process will be always greater than the irreversible. Why? Because of here several number of steps is involving, but in that case only one step, initial, final. Hope you got the idea. And also by the graph I shown here, look, there are so many sub steps involved here. Here there is only one step, P1, P2. But what about here? Look, PI, so many like that is coming. So based on that, in our JEE 2019 question is asked, consider the reversible isothermal expansion of an ideal gas in a closed system at two different temperatures. Temperature is here T1 and T2 at two different temperatures. And one condition is given here, T2 greater than T1. The correct graphical depiction of the dependence of the work done on the final volume. Dependence of the work done on the final volume. That means how our work done is going to depend on the final volume. And look, this work done is shown in the mod. That means whatever work done we are going to write, that work done will be positive. So what we can say here, 2.303 RT log Vf upon Vi, we can write or not? That means from here what thing is clear, that on increasing the temperature, what about the work done? Work done will increase. By that this thing is clear or not? Because work done is directly related from the temperature. So by increasing the temperature, what about the work done? Work done will increase. But what about by increasing the volume? By increasing the volume, at volume is going to increase, work done will decrease. This is we can also write by that uh, 2.303 RT log Vf upon Vi. That means work done will never be negative. Work done is not going to be negative. So we can also write here positive 2.303 RT log Vi upon Vf. So one thing is clear from here, those are the work done. If our final volume is going to increase, so work done will decrease. If final volume is going to increase, that means on the expansion work done will be decrease. But on increasing the temperature, always work done will be greater. And one more thing, there is no any intercept. When we are going to compare that y is equal to mx plus c, what about the intercept? Intercept is 0 in that place. And when we are going to consider about the slope, so slope we can get in that case, m is equal to the 2.303 r. That will be the in past two. I'm going to compare by this expression, that one. So slope will come that one, and what about the and yes, yes, slope as well as temperature will also come here. This because of temperature they are going to change, so we are not going to consider here. And because of at a two different temperature we are going to plot a graph of work done versus volume. So those are the final volume. Look here, it is coming VI by VF. That means final volume is coming in just reverse. By increasing the volume, what will happen? Work done will decrease. So when we are going from this point to that point, work done is going to decrease. In all that condition, this thing is happening. So no doubt here. So only one thing we are going to consider here, temperature. On increasing the temperature, work done will increase. Definitely that is going to show, and intercept will also be not also zero, and those are the line of this, they are not going to intercept. So look, in all that thing they are going to intercept. Here it is going to intercept, here also it is going to intercept, but at that place intercepting point is coming at that place, this is also wrong. So ultimately which one is the correct? C. So C is our correct answer. Next point is coming our Joule Thomson effect. It's a really very important point, Joule Thomson effect. So in that there is a thermometer is placed here, and what is the Joule Thomson effect? So firstly, I want to say one point. Joule Thomson effect is the isoenthalpic. Isoenthalpic. So beta, what is the means of the isoenthalpic? That means change in enthalpy will be zero. So here change in enthalpy coming zero. And also during that process, heat exchange between system and surrounding is not allowed. Heat exchange, heat exchange between system and surrounding, between system and surrounding is not allowed, is not allowed. That means what we can say, that that is the adiabatic condition. What condition? This is the adiabatic condition. In adiabatic condition, what thing we have to write? We have to write heat exchange is equal to the zero. So in that place, what is happening? There is a one wall, that is the part A, and this one is the part B. So what is happening? And one more thing, those are the Joule Thomson effect. It is only applicable for the real gases. What is it? Only applicable for the real gases. It is not applicable for the ideal gases. So any real gas, when it is passing through the porous plug, that means that is one wall. Here we are going to create one small hole, very minute hole. Through that hole, any real gas, its pressure is P1 and that block pressure is P2, and one condition here is P1 greater than P2. So if any real gas from the higher pressure end to the lower pressure end, it is entering through the very minute hole. So what is happening? It is expanding. What is it? Gas is expanding. So if gas is expanding, so who is doing the work? So work done by the gas. During the expansion, work done by the gas, work done by the gas. If work done by the gas, actually externally we are not going to supply any amount of energy. So whatever internal energy present in that gas, it is going to convert in form of the work done. So whatever internal energy is present, it is going to convert in form of the work done. That means when work done by the system, so it is decreasing its internal energy. What is happening? Decreasing its internal energy, decreasing its internal energy. Because it is decreasing its energy, so it will show the cooling effect. What it will show? It will show the cooling effect. It will show the cooling effect, and it is called the Joule Thomson effect. What we are telling, it is called the Joule Thomson effect. So what is the Joule Thomson effect? Once again, I am going to explain that. That is the isoenthalpic process. That means throughout the process, enthalpy is not going to change, and heat exchange between system and surrounding is not possible. So in that under that condition, if any real gas passing through the minute hole from the higher pressure end towards the lower pressure end, we are experiencing the cooling effect. Why this cooling effect is coming? Because of the work done by the gas. So whatever internal energy contained by the system, that is going to convert into the work done. That is why we are experiencing the cooling effect. During expansion, the enthalpy of system remains constant, and Joule Thomson coefficient we are writing by that mu Jt is equal to dt upon dp at constant h. So there is some condition here is given, that cooling effect. That means if Joule Thomson effect is coming positive, if Joule Thomson effect is coming positive, so that is the expansion case. What is the expansion case? If anywhere Joule Thomson effect is coming positive, so gas will show the cooling effect. If Joule Thomson effect is coming negative, that means this is under contraction, not expansion. This is under contraction. So gas will show what? Heating effect. If mu Jt is coming negative, so gas will show the heating effect during the contraction. If Joule Thomson effect is coming zero, that means gas is not going to show the neither cooling effect or heating effect. So Joule Thomson effect is always coming zero for the ideal gases. For the ideal gases, Joule Thomson effect is coming zero. So thing is arising here, actually why Joule Thomson effect is coming zero for the ideal gases. This is because of ideal gases cannot be compressed. What is it? This is because of ideal gases. Ideal gases cannot be compressed. Ideal gases cannot be compressed. This is a thing. So sometimes they are asking, actually what is the inversion temperature? If any gas having the higher inversion temperature, so what will happen? So the temperature at which Joule Thomson effect is changing from negative to the positive, such temperature is termed as the inversion temperature. What is that temperature? The temperature at which Joule Thomson effect is changing from negative to positive, such temperature is called the inversion temperature. And what is the inversion temperature? It is the temperature below which a gas becomes cooler on expansion. It is the temperature below which gas becomes cooler on expansion. That means each and individual gas having its inversion temperature. So once inversion temperature is going to be lower, that means suppose that that is the inversion temperature point. Any gas having the inversion temperature, for example, 25 degrees Celsius. Once we are going to convert it into 24 degrees Celsius, so immediately it is going to show the cooling effect. But it is going to show the cooling effect. Any gas having the temperature, suppose 25 degrees Celsius, we are going to decrease the temperature up to 24 degrees Celsius. So gas will show the cooling effect. And more than that temperature, gas will show the heating effect. That means if any gas is having higher temperature than the immersion temperature, so we cannot liquefy that gas. Any gas having the higher immersion temperature, any gas having the temperature more than the immersion temperature, so gas can never be liquefied. And sometimes question is coming, actually those are the hydrogen and helium gas. Why they are going to show the heating on expansion? Those are the hydrogen and helium gas. On expansion they are going to show the heating effect. On expansion they are going to show the heating effect. So that is the two exceptional cases. all that real gases whatever is coming on expansion, they are going to show the cooling effect, but hydrogen and helium on expansion they are showing the heating effect. Why this thing is happening? First point, their inversion temperature is negative. Look, most of the gases, those are real gases, their inversion temperature is lie around the room temperature, so that means that is the positive. So, but in case of the hydrogen and helium, their inversion temperature is very, very less. Look, minus 80 degrees Celsius and minus 240 degrees Celsius. So that is why on expansion, they are going to show the heating effect. Apart from that, those gases, they are going to show the cooling effect. And those gases having the lower inversion temperature than the room temperature. What is that? You can make one note. Those gases having lower inversion temperature, lower inversion temperature will show will show heating on expansion, will show heating on expansion. So look, like for the hydrogen, what is the inversion temperature? That is coming minus 80 degrees Celsius. So minus 80 degrees Celsius temperature, it is a less than the room temperature. So those gases having the lower inversion temperature than the room temperature, so on expansion they are going to show the heating effect. So thank you student. Hope that lecture will be the useful for you. For getting such type of lecture continuously, subscribe my channel.